Hello everybody, I'm doing some experiment with a day-night cycle inside my engine, and so I created this simple test scene to see if my calculations were some way correct. Of course it's just a simplification of a real system, but it's nice to see that some things act as expected. Okay. Here we can see a simple basic solar system where we have just the Earth and the Sun, and we can see here a set of controls that allows to set various time parameters. For example, you can change the time of the day, and you will see that the Earth rotates around its axis. We can see here that the time of the day is related to Greenwich, to the meridian of Greenwich, and here this cursor points to a place on the Earth, and it's at the latitude of Greenwich. So it's located in Greenwich, and here we can rotate also the Earth around the Sun. But with this control we can rotate it, but leave the time of the day unchanged. So for example, if we rotate here, we can see that the Earth is facing the Sun always from the same side, just like the Moon does with the Earth. And because the time of the day remains the same, so in Greenwich, which will be always noon. We can rotate around the Sun, we will see that always the same face is facing the Sun. Here we can rotate both around the axis and around the Sun, just like it happens in real life. And we can see how the Earth rotates around its axis and around the Sun simultaneously. It's nice to see how the season work. For example, here we can see that in the northern hemisphere we are in summer, because here we are in winter, because we are in January, 1st of January, and we can see, for example, that on the North Pole never receives the sun during winter. We can change the time of the day, and we can see that the sun never reaches the North Pole. On the opposite side, when it's summer, for example, summer in the northern hemisphere, of course, so for example near the solstice of summer, we can see that the North Pole now is facing the sun, and if we change the time of the day, we can see that the sun never leaves the area. It's always facing the North Pole. Here we can see that it's summer, this is the Earth axis, and since it's summer in the northern hemisphere, we can see that the sun rays, now this is oversimplified model, so the distance is not realistic, but the sun rays will arrive very perpendicular to this area, and less perpendicular to the southern hemisphere, where it will be winter. Here we can also see that since the parallel are like this, or in the northern hemisphere, the major part of the parallel will be covered by light, so the duration of the day is longer than the duration of the night. And for example, in spring and in autumn, we will have half of the parallels covered by sun and half of the parallel covered by because it's perpendicular, so the day and the night will be of the same length. We can also see an animation of the system in action, and here you can see you can change the speed of the simulation. Here we choose how much a day will last during the simulation. So here, for example, we selected that 1 day will be reduced to 1 second. So the Earth will do a complete rotation around its axis in just 1 second. You can see it. And at the same time, now it's not very easy to see it, but it's also rotating around the sun, as you can see here. Using the result obtained at the previous step, we can now use those results inside my terrain rendering. Here we can choose the latitude, like we are selecting where this terrain is positioned on the globe. So for example, in this case, it's positioned in a latitude like, for example, Rome, 45 degrees on the northern hemisphere. Here, if we change the latitude, it's like we are moving our terrain on the surface of the Earth, and then we are moving it on the north, towards the North Pole. And on the opposite side, here, when we reach 0, it's like we are moving the terrain on the equator line. And going on the other side, we are moving it on the southern hemisphere towards the South Pole. Okay, let's get back to 45 degrees of latitude, so like in Rome, Mediterranean area. And we can see, for example, that since we are in January here, even if it's noon, 12 in the day, we can see that the shadow, the mountains cast a shadow, so the sun rays are not perpendicular to the surface, but actually there is a shadow cast on the north side of the terrain. So you can see that even if the time of the day changes, there is always a part that is facing the sun, and another part receives less sun, which is the north part, since we are in the north hemisphere. If we change the seasons, for example, we can see that, for example, in summer, the cast shadow is almost inexistent because the sun rays are very perpendicular to the surface. And then, going again to the winter, the north part receives less light. We can use those information, for example, to improve snow placement across the map. For example, we can choose to place more snow in those areas that receive less light. For example, if we don't take into account those information, when we place snow, we will see that it's evenly distributed across areas of the map. The south and the north receive the same probability to get snow. But if we take into account also those information, for example, we can generate a shadow map that takes into account which areas receive more light and which areas receive less light during the day, we will see that the result is different. Okay, now it's too much snow, but okay, we can see that the north area of the north-facing areas of the mountains receive more snow, and the south-facing areas receive less snow because they will receive more light, and so snow is more likely to disappear during time. For example, if also we change elevation, then the shadow of the mountains will be longer, and so we expect also to see significant changes in the snow placement. We try, for example, and then we can see that there is more snow because the shadows of the mountain is longer, and those areas will receive less light during the day. If we change, for example, During the day, we see that this area, for example, receives light almost all the time, and this area, for example, never receives light during the day. To get a more realistic visualization, we can also apply hydraulic erosion. We can see the erosion process in action. You can see how river forms and form lake. Okay, we can stop it now. Oh, looks more realistic. And now we regenerate again the shadow map to take also into account the variations of the map due to hydraulic erosion. For example, here we can see that the snow placement takes also into account the eroded areas that creates some valleys that we receive less sunlight, so they are more likely to accumulate snow during the day, for example. You can see that looks quite realistic. Let's see what those considerations imply when we see the scene from the surface of the Earth point of view. For example, here we are at latitude 42 in the northern hemisphere, and we are in winter, and we can see that during winter the trajectory of the sun stays very low in the sky. We can simulate it and see that during the whole day from sunrise to sunset, the sun doesn't go up very much. If we change the day of the year and we go towards summer, we see that the sun follows a higher trajectory. This is explained, for example, here. The summer arc is much higher than the winter arc, and the sun follows a trajectory inside this solar window. So this is at the solstice of winter, and this is the solstice of summer. And from winter to summer, the trajectories of the sun fit inside this area. A very interesting thing is that if we plot the sun position every day in the whole year, always at the same hour, it describes this H-shape trajectory. We can see it here. This is called an alemma, and this an H-shape described by the sun, taking a snapshot of the sun position every day of the year, always at the same hour. Since here we don't change the time of the day, but we change only the day of the year, we are doing basically the same. And we can clearly see that it follows that H shape. We are facing towards the south, and we see that we change latitude. If, for example, we go towards the North Pole, the sun gets lower and lower. And for example, in winter, near the North Pole, we can change the time of the day, but we'll never see the sun during the day. It always stays below the horizon. On the opposite, on summer, it never goes below the horizon, so it's always daylight. There's always daylight. The fun thing is that during summer in the North Pole, you can see that the sun does not do parabola, but rotates in circle around the North Pole. Never goes down and stays almost always at the same altitude in the sky. It's very interesting. I didn't expect to see it like that. Of course, this is just an approximation. I didn't take into account a lot of variables, and I did many simplifications. For example, the orbit of the Earth around the Sun in my system is just a perfect circle, but we know that in reality it follows an elliptical trajectory. And also the shape of the Earth in my system is just a perfect sphere, but we know that it's not a perfect sphere in real life. But despite all those approximations, it's nice to see that the resulting values are not so different from what you would expect. For example, we can compare the time of sunset and sunrise in various places, and we can see that they are different, but not so much from the reality. For example, we know that here we are at the longitude of Greenwich. We can set also the latitude of Greenwich, so we will be placed like we are in Greenwich. This is the latitude of Greenwich. We reduce the mountain's elevation so we can clearly see the horizon. Okay. For example, we put the current date, April 22, as the day of the year, and we can see the time the sun rises. Okay, like 5 in the morning, and the actual values are 5:46, not perfectly exact, but not so different. And the sunset is about at 19, and the actual sunset is at 20, so 1 hour error. Not so little, but considering all the simplification, it's not so much error. For example, the length of the day is almost the same as expected. Okay, I think it's enough for now. I hope you enjoyed the video. It was a bit longer than usual, but I still hope that you could find something interesting in it. Have a nice day. Bye bye.